All right, today we're going to talk about logarithms. Hold on. Hold up. Logarithms. Logarithms are one of like the fundamental operations. You know, you probably have a log button on your calculator. Although a little mysterious. I hope that you've like heard of logarithms before. Although I'm gonna behave as if you don't know anything about logs, just in case. You know, my experience. A lot of people learn about them in high school, but still feel a little fuzzy about them. I'm gonna try and shave off the fuzz, as it were. Hopefully everybody's going to feel fine about logarithms. You may know that there are logarithms with lots of different bases. Let's start off with the common log, which is the base 10 log. Sometimes people write it as log with a little 10 there. Sometimes people just write log for this. This is called the base 10 log. Base 10 logarithm, or also called the common logarithm. And what it means, I'll tell you what it means. You plug some number in there, and it tells you what is the exponent. So here's like the definition. Log base 10 of x means there isn't really a formula for it. That's why you have a button on your calculator. There isn't another formula for the log. It is its own thing. But what it means is, it means the exponent in 10 to what power equals x. All right. So when you're trying to find the log of a number, you have to try to figure out what exponent would make 10 to what power equal that number. For example, this is very easy if you have just like, powers of 10 basically. What is log base 10 of 100? You got to think to yourself. Okay, I'm going to write the answer here, but can I just like think off to the side? What I have to think to myself is 10 to what power equals 100? And this, I suppose you just have to guess, right? What is it? 10 to what power equals 100? I think the answer is 2, right? 10 to the 2 is 100. So the log base 10 of 100 is 2. All right, how about log base 10 of 10,000? You should think to yourself, 10 to what power equals 10,000, right? And the answer here would be 4. 10 to the 4th power is 10,000. This is 4, all right? Basically, what the log is counting is sort of how many digits are in the answer, although it's one less, right? This is a 3-digit number. Its log will be 2. You don't get up to a log base 10 equals 3 when you get up to 1,000, right? Then the log is 3. When you get up to 10,000, the log is 4. It's measuring how big the number is, but it's in terms of the digits, not in terms of the number, the actual value of the number itself. All right, so this is what I just said. The log base 10 of 10 is 1. That's because 10 to the 1 equals 10. Log base 10 of 100 is 2. That's because 10 to the 2 is 100. What about the log base 10 of some other number like, 89, right? What is this? The answer is, this is not an answer that you can just do in your head. You basically have to use a calculator if you want to compute this logarithm. In the old days, logs have been around for a while before calculators were invented. You would just buy a book. There were like giant books full of logarithms of like every number you could think of. They just told you the logs of all the numbers. Not very efficient, but it takes a lot of work to create such a book. But once you have it, you can figure out the logs of whatever you want by looking them up in the book. Anyway, what can we say about this? Well, we can say it's like a little bit less than 2, right? It's somewhere between 1 and 2 because the log of 10 is 1, the log of 100 is 2. This is in between. Don't worry, I tested negative. This 89 is in between 10 and 100. I suppose it's closer to 100. So I'm going to say this is, you can't say exactly unless you use your calculator, but I'll just say between 1 and 2. Closer to 2, right? Okay, these have all been the log base 10, all right? The answers here are according to the exponents 10 to what power equals this number, all right? This is called the log base 10. Now, there are other logs. You can do the log with any base. Let's just talk about some other logs with other bases. How about this? Log base 2 of 8. This is the same, only instead of thinking about powers of 10, you got to think about powers of 2. So the question here is, what you need to think to in order to figure this out is 2 to which power equals 8? Well, what do you think? Is 8 a power of 2? Actually, 8 is a power of 2. 2 to the third power is 8. So the answer here is 3. It's because this 3 is the number that would go right there. 2 to the third power equals 8. All right? This is the log base 2. And the log base whatever, this number is always the base of the exponent down here. This number is the answer, and then this 3 is what appears in the exponent to make that equation true. All right? Log base 2 of 8 is 3. How about what's log base 2 of 64? Well, for this, you have to think 2 to what power equals 64. 2 to the third is 8. 2 to the fourth is 16. 2 to the fifth is 32. I'm doubling each time. 2 to the sixth is 64. And so the answer here is 6. All right? It is the question, when you see log base 2 of some number, the question is 2 to what power equals this number? And it is a fact. 2 to the sixth power equals 64. All right? This is how you do a log with a different base. The log base 2 is an important one. The log base 10 is actually not so important. It's called the common log, but that's only because you can kind of guess the values in your head. This is harder to guess the values in your head. How about, here's a weird one. Log base 3, actually, here's one that's not so weird. Log base 3 of 9, what do you say? The question is 3 to what power is 9? And the answer is 2. 3 to the 2 is 9, and so the answer to the log is 2. Here's one that's a little weird. What is log base 3 of 1/9? Log base 3 of 1/9. This means, of course, 3 to which power equals 1/9. Can you write 1/9 as a power of 3? Here's a hint. Since you have a fraction here, the number is in the denominator, you should expect this to involve a negative exponent. And now that I say that, I hope you realize, oh yeah, 3 to the negative 2 is 1/9, right? 1/9 is the same as 1 over 3 to the 2, which is the same as 3 to the minus 2. And so this little question mark here, its value is minus 2. And so the answer, log base 3 of 1/9 is negative 2. Really is. There is one very special logarithm that we are going to use probably more often than the others. It is important, especially in calculus. It is called the natural logarithm, or the natural log, and it is written this way, ln of x. The natural log is just the same as all the other logarithms, so this is the same, but the base is this fancy number, the special number, e. All right, the base is e. Otherwise, it's the same as the other logarithm. So when I see something like ln of 8, it means what is the exponent? Ln of 8 is some number. You should think about what is the number such that e to some power equals 8. And this really, you cannot try to do this by hand because e is already like an irrational number. There's no nice exponent you can put here that would give you the number 8. But this is the idea behind how you would find ln of 8. In the real world, how you would find this is you just hit that button on your calculator and it will tell you the natural log of 8. All right, some things that we can do, really the only values of the natural log that you can figure out by hand are values in which you're trying to find what is the natural log of something which is already like e to some power x, I'll say. This means what is the exponent in e to some power that makes you get e to the x? And the answer is x, like x is already the exponent. So this right here is x. This is worth remembering. The natural log of e to some power is always equal to that power by itself, all right? This is like a fundamental fact about the way that the natural log works. One more fundamental fact about all logarithms. Sorry, I got 2 more actually. 2 big facts. The first one is simple. These are true of any logs with any base, so I'm going to write it this way. log with base a, whatever the base is. What is log with base a of 1? Actually, this you can always say very easily what the log base a of 1 is. If you don't know this rule already, you would think of it in this way. Log base a of 1 means a to which power equals 1. Can you guess the exponent in there? I hope you can. If you remember something about exponents, you will remember. Anything to the 0 power equals 1. And so that is 0, right? So that means the log base a of 1 equals 0. Why this is true? It's because a to the 0 equals 1. And so this is my first big log fact. All right, this one is easy enough to see why it's true. The next one is not as easy to see why it's true. Would you mind if I just tell you what it is? The next one actually is super useful. In fact, this rule is the principal reason why the log is useful for anything, at least in terms of what we're going to be doing with the log in this class. Here's the rule. The log base a of some exponential function is like this. You can move the exponent down in the front. That's what this rule says. This is actually the rule which, for our purposes in this class, makes the log useful for something. It means that if you ever have a variable inside of an exponent, you can use the logarithm to move the variable out of the exponent. This is something that is really not possible to do any other way. If your variable is inside the exponent and you want to get that variable out of there so you can solve for it or something, this is the rule to use. All right, these are two big facts. Like I said, these work for any base, no matter what the base is. In particular, they work when the base is the number e, which is when you are talking about the natural log. So I'm just going to write the same rules again. They are also true of the natural log because the natural log is the same as one of these where you choose the base to be e. So it is a fact. The natural log of 1 equals 0. You can try that on your calculator if you don't believe me. And also, this is a fact. The natural log of something to a power is the same as if you move the power down front, take the natural log of the base. Using logs, you know, logarithms were invented like in the early 1600s by a Scottish guy named Napier. What's the point of that? Like, it's a weird operation. You basically have to use a calculator to do it most of the time, unless you get lucky. They are actually useful for solving certain types of equations, and I just want to do some examples of that. They are useful for solving for x inside an exponent. It is important to be able to do this whenever you're doing like a real world problem which involves exponential functions, and exponential functions do occur fairly often in real world problems. So you use logs to solve for x when x is inside the exponent. So for example, if I had something like this, and your job, solve for x. All right? Can you solve for x here? Well, the x is inside the exponent. The first thing you want to do is just isolate the thing which has the exponent in it. So I'm going to say isolate the exponential part. In this case, that's easy to do. You subtract the 5. So I get 3 to the 2x equals 75. All right. And now the trick is take the log on both sides. It really doesn't matter which log you use, although I'm always going to use the natural log. So I'm going to do natural log 3 to the 2x equals natural log of 75. And now we're going to use that rule that I said before, the rule about natural log of b to the power x equals x ln b. Whenever you have an exponent inside of the natural log, you can bring it down to the front. This is the beauty. This is the trick. This is like the whole reason, from this point of view, the reason for the log to exist at all. It is a trick which allows you to move the variable out of the exponent, and that will let you solve for x eventually. Otherwise, the x is like stuck in there. How do you get the x down from there? This is how you get the x down from there. You do the log on both sides. Now I can move the exponent out front. 2x ln 3 equals ln 75. And now we can solve for x by dividing. This ln 3 is a number. You can put it on your calculator if you want to. The 2 also, of course, is a number. So I can say solve for x. X is ln 75 divided by 2 ln 3. There you go. I solved for x, didn't I? If you want to know what that number is, like as a decimal, plug all of this into your calculator. Let's do one more of those. This one's going to be a little bit harder. 4 to the power 3x plus 2 equals 10 to the power x. Solve for x. All right. Like I said last time, first you should isolate the exponential. So this time we have two separate exponentials, but they are already isolated, so we don't have to do any funny business first. I'm going to immediately take the natural log on both sides. ln 4 to the 3x plus 2 equals ln 10 to the power x. Do the trick with the exponents moving down into the front. So this exponent comes down front. 3x plus 2 times ln 4 equals, here, x times ln 10. All right, and now we just have to solve for x. X is not inside the exponent anymore. Got my little, I just washed the windows. I should put that away. Just leaving random stuff lying around. Doesn't it look clean? I washed it. It's getting a little doity. Okay, I got to solve for x here. These are all numbers here, right? All I have is x times some numbers. I got addition here. It's a little tricky. How do you actually get the x all by itself? I want to put everything which has an x on it on one side and all the constant stuff on the other side. Before we try and do that, you really have to distribute right here. It's going to say 3x ln 4 plus 2 ln 4, right? I like distribute like this, right? Equals x ln 10. Now I have three things, like I said I was going to do. I'm going to put all the ones with x is on them on one side and all the other ones on the other side. Let's put the x stuff on this side. So 3x ln 4 can stay here. This guy I'm going to move over here by subtracting it. Minus x ln 10. And this guy I'm going to move over here by subtracting it. Negative 2 ln 4. All right. Almost done here. I need to solve for x. I have these two things, both have an x in them. You can factor the x out. Doing some fairly sophisticated algebra here. Finally, we can get the x by itself by dividing that thing. X equal minus 2 ln 4 divided by 3 ln 4 minus ln of 10. There you go. This is the solution for x. Again, if you wanted this like as a decimal, you can plug all that into your calculator. I don't care about that. Now that we know all about that, let's try. Let's just do one more of those. But this is in the context of a real world, applied problem, just to convince you that this really is important for something. Do you remember my made-up example about the pandemic last time? This was a function which is supposed to represent the number of people who have the infection after day or on day t, right? This is the number with the infection on day t, all right? At day t equals 0, 50 people had it, and then it spreads. The rule was the size of the infection increases by 1% every day. And this was the formula. Here's a question we could ask. This is a very natural question. I hope you'll agree. How long until 100 people are infected? All right. Obviously, you would want to be able to answer questions like this if you were trying to model the spread of a disease. How long until 100 people are infected? Well, the question here is, really, what is the t which makes this thing equal to 100, right? This thing represents the number of infected people. We want to set that equal to 100 and solve for t because t is the time. So we are going to do something like 50 times 1.01 to the power t equals 100. Solve for t, right? Can we solve for t? Yeah, actually, we're going to use a log, but this is a standard type of example. Here's the exponential part. I need to isolate this first, so we're going to have to divide by 50 to get that out of there. So it's going to be 1.01 to the power t equals 100 divided by 50 is 2. Even I know that. Now to solve for t, you do the log on both sides. ln 1.01 to the t equals ln of 2. Move the t out front like we always do. T ln 1.01 equals ln 2. And finally, we can divide by this log to solve for t. T is ln 2 divided by ln 1.01. There you go. Now, I always say, if you care about this answer, you can plug that into your calculator if you want. I actually plugged this one in just because this is I wanted to know what the real number was. The number that I got when I plugged this in is 69.66, etc. This is some irrational number. All right. So what's your interpretation of the answer here? It means 100 people will get infected, I guess, like in the middle of day 69. That's what this answer means. On the 69th day is when we expect the 100th infection to occur. Pretty good. Not good for that guy.